Hi everyone, welcome to the next episode for this. So we're going to be doing a calculus-based problem for the start. So if you're not doing that, just skip this problem. And what we know for this calculus-based problem is we have omega t is equal to 2 minus 2.1 t squared. What is the angular acceleration of the blade at t equals 9.1? So what we should know is for velocity, if you find the derivative, you get acceleration. That's going to be the same thing. If we find the derivative of the angular velocity, that'll give us alpha or angular acceleration. So we can say alpha t equals to this derivative. So this is going to be 0 minus, and then this 2 is going to go over here if we use the power rule, minus 4.2 t. Okay, and then we want this at 9.1 seconds. So it's going to be negative 4.2, 9.1. And this is going to give us a value of 38.22, negative 38.22 radians per second squared. Okay, let's look at the next problem. A horizontal disc rotates about a vertical axis through its center. Point P is midway between the center and the rim of the disc. So we have point P right here. Okay, and Q is on the rim. Okay, so we have Q over here. Okay. If the disk turns with a constant angular velocity, which of the following statements about it is true? P and Q have the same linear acceleration. No linear acceleration, because remember, it's going to be accelerating more linearly at the end because it's traveling a further distance. Q is moving twice as fast as P. Okay, maybe. The linear acceleration of Q is twice as great as the linear acceleration of P. Oh, okay. The linear acceleration of P is twice as great as the linear acceleration of Q. Okay, so we know that this one won't be going faster, so it can't be D. And then E, the angular velocity of Q is twice as great as the angular velocity of P. Okay, and we also know that's not going to be correct because the angular velocity at every single point is the same. Okay. So Q is moving twice as fast as P. So we should know speed is equal to omega times R. And since it is twice as far, it is going to go twice as fast. But we should also know the same thing. Alpha is equal, linear acceleration. Linear acceleration is equal to alpha times R. And again, since it's twice as much, it's going to have twice as much acceleration. So it's going to be B and C. Okay, so when we're looking at this, it's going to be B and C. All right. A 1.15 kilogram grinding wheel, 22 centimeters in diameter, is spinning clockwise at a rate of 20 revolutions per second. When the power to the grinder is turned off, let me actually kind of underline certain things. 22, 20 revolutions per second, sorry. When the power of the grinder is turned off, the grinder wheel slows with a constant angular acceleration. It takes 80 seconds to come to rest. What was the angular acceleration of the grinding wheel as it came to rest as if it were taking clockwise rotation as the positive? Okay, so let's see what we know. We know omega initial is equal to 20 revolutions per second. We also know that it took 80 seconds to come to rest. And we know the final angular velocity is 0. And what we're looking for is angular acceleration alpha. Okay, so this one's a little bit tricky. We could find the answer in revolutions per second squared, but it's asking what was the answer in radians per second squared. So that means we should change this to be radians per second squared. So we're going to do a little bit of dimensional analysis here. We should know that 1 revolution is equal to 2 pi radians, because 1 time around is equal to 2 pi radians. So I can get rid of that and get rid of that. And what I get is I get 40 pi radians per second. Okay. Now that I have that, let's try to find what the alpha is. We know alpha is equal to omega final minus omega initial over t. Alpha, which we're looking for, omega final is 0 minus omega initial, which is 40 pi. Divided by t, which is 80. So this is going to be equal to negative 0.5 pi. But if we were to put this in the calculator, we get 1.57 negative 1.57 radians. negative 1.57 radians per second squared. Okay. Part B, how many revolutions did the wheel make during the time it was coming to rest? Okay, so we're going to look for the change in theta, which is equal to omega initial t plus 1/2 alpha t squared. Actually, I think this one, we can do this one. How many yeah, okay, but let's do this one. So omega initial is 40 pi, time is 80 seconds, plus 1/2. Acceleration we found is negative 1.57, and t is 80 squared. So doing this, let's find how many radians. So 80 squared times 1.57 times 0.5 minus 80 times 40 pi. And then we get 5,029 radians. However, it says how many revolutions. So we know this is radians. So let's get rid of this radians and get into revolutions. So we're getting rid of radians, revolutions. And again, we should know 1 revolution is equal to 2 pi radians. So we're going to do 5,029 divided by 2 pi. Make sure to put in parentheses. And we get 800 revolutions. Okay. All right. So let's look at this next one. This is the last one. A 3.45 kilogram centrifuge takes 100 seconds to spin up from rest. Okay, let's see. 3.45 takes 100 seconds to spin up from rest to its final angular speed with a constant angular acceleration. A point located 8 centimeters from the axis of rotation of the centrifuge moves with a speed of 150 meters per second when it is at its full speed. Okay, what is the angular acceleration of the centrifuge as it spins? Okay, so let's see what we know. We know time, 100 seconds. We know it spins from rest. Omega initial is 0. And what we're looking for, the angular acceleration. All right, so we only have 2 pieces of information for the kinematics, and we need one more. So what we should know is we have the final velocity here. So, and we also have this 8 centimeters here. So what we can do is we can use part of that knowledge to find what the omega final is. So what we can do is we can find this omega final r is equal to velocity final. So we know what velocity final is. That's going to be 150. We don't know what omega final is, but we do know that the radius is equal to 0.08, 8 centimeters, which is equal to 8 meters. So we get omega final, 150 divided by 0.08. And we get 1,875 radians per second. I mean, yeah. Whoops. I mean, these things spin really, really fast in the medical industry, so I'm not too crazy about that. Oopsies. Sometimes this gets a little glitchy. Let me just do this. Divided by 7 seconds. Okay? But now we have 4 pieces of information. We have time, we have omega initial, we have alpha that we're looking for, and we have omega final. So now let's just do alpha is equal to omega final minus omega initial over t. Omega final 1875 minus 0 t 100. And what we get is 18.75 radians per second squared. Okay. Part B. How many revolutions does the centrifuge make as it goes from rest to its final angular speed? Also, how many revolutions does the centrifuge make as it goes from rest to its final angular speed? How many revolutions? Oh, how many revolutions? Okay, so we're looking for a change in theta. Okay, so let's do this. Change in theta is equal to omega initial t plus 1/2 alpha t squared. So this is going to be equal to 0 plus 1/2 alpha t, 18.75, t squared, t swift, 100 squared, which is going to be equal to 100 squared times 18.75 times 0.5. 937.5 radians. But let's change this to be revolutions because that's what it's asking for. 1 revolution is 2 pi. So that means it's going to be equal divided by 2 pi. And we get 149.2 revolutions. 149.2 revs in 100 seconds. Okay, yeah, that did seem a bit off. Okay, let's put this in my calculator. 100 squared times 18.75 times 0.5, and I get, a huge number, 93,750 radians. Remember, this is radians, so let's get this into revolutions. Revs, radians. 1 revolution, remember, is 2 pi. So we're going to divide this by 2 pi, make sure to put in parentheses, and we get 14,921 revolutions. Alright everyone, let's look at this next problem. This one could be kind of difficult. So we have a 1.25 kilogram ball being rolling from rest with a constant angular acceleration down a hill. It takes 3.6 seconds for it to make the first complete revolution. How long will it take to make the next complete revolution? So this is pretty difficult, I would say. There's a lot of things going on. So this ball starts from rest and it's going to roll 2 times. What we want to know is how long it's going to take to roll the second time. We already know how long it takes to roll the first time. That's going to be 3.6 seconds. Okay? So we want to know how long it's going to take to roll the second time. It should be less than this because what we know is it's going faster and faster and faster as it rolls down, so it should be less. So let's see what we know. How I'm going to try to do this, there's many ways of doing this, but I'm going to try to find out how long does it take to roll the whole time 2 times. Okay, so that's pretty much what I'm trying to find out. T1 and T2 combined. So what are we looking for? Time. Initial angular velocity is 0. We know it's going to roll twice, so displacement is going to be 2 pi times 2, which is 4 pi. 4 pi. And that's what we have. So that's what we're trying to find, but we don't have enough information to find time. So what we're going to do is we're going to see if we can find, maybe we know more information just from what happens from the first roll. So from the first roll, we know omega initial is 0. We know it takes 3.6 seconds to make 1 full revolution, and we know 1 full revolution is equal to 2 pi. And now let's try to find something that's for here and here that's the same. And what's that going to be? The constant angular acceleration down the hill. So let's find what the angular acceleration is. Now that we know that, let's do displacement is equal to omega initial t plus 1/2 alpha t squared. This is going to be 2 pi is equal to 0 plus 1/2 alpha t 3.6 squared. Let me put this in my calculator. 2 pi times 2 divided by 3.6 squared. And I get alpha is equal to 0.97 radians per second squared. Okay. Now that we know that, let's try to find out what this total time is. So I know delta omega initial t plus 1/2 alpha t squared. This is going to be 4 pi is equal to 0 plus 1/2 alpha, which we found was 0.97 t squared. So 4 pi times 2 divided by 0.97, we get this is going to be equal to the time, which is 5.09 seconds. However, this is just how long it takes to go 2 revolutions. So we just want to find out what this part is right here. So I'm just going to subtract that from the 3.6 seconds. And what I'm going to get is 3.6, 1.49 seconds. Okay? And that's how you do it. There's other ways of doing it. You could have found what the velocity is when it starts to roll over here. and then use that as the initial velocity. But I think this is the easiest way, but you could have done it a different way as well. All right, let's look at this. The figure shows a graph of angular velocity. So the angular velocity, I'm not sure what color this is. I think it's green. I'm colorblind. And then what we have is we have an angular acceleration versus time for a particular rotation. During which time interval is the rotation speeding up? Okay, so this could be kind of confusing when you look at it at the beginning. It's like, okay, what's speeding up here? However, let's just take a little bit of time with this. So let's just look at the omega. So we know that there's imaginary numbers here. Let's just call it 1, 2, 3, and then we'll call it -1, -2, -3. So if it goes from 0 and it gets higher for the omega, we know that it's speeding up. So from 0 to 2 seconds, it's going to be going faster. It goes from 0 to 2. So we know it's going to be going faster from 0 to 2. And then, so that's one of them. And then, but we also know, so from here, it's slowing down to 0. So it's not going to be going faster here. And then from here, it's going from 0 and it's getting faster and faster in the other direction. So it's going to be from 4 to 6 seconds, also speeding up. Okay, so we know during those two times, from 0 to 2, and then from 4 to 6, they're getting faster. During which time interval is the rotation slowing down? And again, we can just say from 2 to 4, it's when it's slowing down. Okay, because now we're going from what we said is 2 meters per second to 0. Okay, now it goes from 0 to negative. So negative is a speed, so don't get confused by that. I know it gets a little confusing. All right, so let's look at this last problem. You finish playing a CD. This angular velocity at t equals 0 is 27.5 radians per second. And its angular acceleration is a constant -10 radians per second squared. What is this angular velocity at 0.3 seconds? Okay, so what we want to find is, we want to find what the final angular velocity is, because we want to find it after 0.3 seconds. We're after 0.3 seconds. Initial angular velocity, they gave it to us, is 27.5 radians per second. And alpha is -10 radians per second squared. This is part A. Okay, so now let's use our formula. We can see, we can use the V final formula, or omega final is omega initial plus alpha t. It's going to be equal to 27.5 plus -10 times 0.3. So let's see what we get for this. 27.5 minus 3, 24.5. I could have done that on my own. Radians per second. Okay, part B. What angle does the line PQ make with the x-axis? Okay, so we want to find the angle, not radians or anything like that. We want to find the angle. So this one's going to be a little tricky. So let's find a theta. So theta is equal to omega initial t plus 1/2 alpha t squared. So this is going to be equal to, ooh, this might be a little complicated. No, it should be fine. 27.5. T is equal to 0.3 plus 1/2 alpha -10, 0.3 squared. 0.3 squared times -5 plus 27.5 times 0.3. And we get, this is equal to 7.8 radians. However, we want to change this to an angle. So what we should know is radians into angle, or degree. I'll put degree here. We should know that 2 pi is equal to 360 degrees. So this will give us an answer of 7.8 divided by 2 pi, putting in parentheses, times 360, to give us 446.9 degrees. So that means it goes one time, and then it's going to go an extra 116 degrees. So it's going to go like over here. 116.9 degrees. Oh, whoops. Sorry, not 116. This should equal 86 86.9 degrees if we minus this by 360 degrees. So this is going to be 86.9 is going to be around here. Okay, 86.9 degrees. All right, guys, thanks for watching. Next time we'll be doing torque, or more like Newton's laws version of angular motion.